take them together.
All right, welcome back, everyone. We're almost at Thanksgiving. Please don't stop all your hard efforts during Thanksgiving. Today we're gonna finish up 15.4. We're gonna get started on 15.5. 15.5 should look very familiar. It is effectively 14.4, but with a splash of seasoning. We add a function to the interval. So if you weren't doing well on double integrals and triple integrals for chapter 14 and you feel like you didn't get enough practice, well, you're going to get more in chapter 15. In fact, from here on, double integrals are a way of life. We have the divergence theorem, we have Stokes' theorem, we've got flux coming up. There's lots of uses of surface integrals or double integrals in the very, very near future. But that's 15.5. Let's finish up 15.4. There's a couple other uses for Green's theorem. One of them is you can find area. We've shown other things where you can find the area. We can find the area inside something if we have the line going, the curve going around it, using the function you can see on the screen. So it's 1/2 the closed line integral of negative y dx plus x dy. Just give you a second to write it down. Now, the area of the ellipse is well known. What is it, pi AB or something like that? I think it's pi AB. But we're not doing the full ellipse. We're doing up to t naught. So t is acting like theta. In fact, we could easily use theta here. But we need to fill in the components of this thing. We've got y and x. We know what those are, but we need dx and dy. So dx is going to be negative a sine t. And dy is going to be b cosine t. I'm missing a dt. And dy will be b cosine t dt. And we're going to integrate from 0 to t naught. Now on a full ellipse, 0 goes up to 2 pi, just like the circle. But we're going to stop short. But when we're done, we can plug in 2 pi for t naught and see what the formula for the equation for the ellipse is.
You need the 1/2 or no?
Yeah, I need the 1/2. And it's a closed line integral. And we've got negative y and negative y. Y is b sine t. I'm going to use a bracket. Negative b sine t. And then I need dx, and dx is negative a sine t dt. And I've got plus x. That's a cosine t. I need to make my parentheses look a little bit bigger. It's starting to look like a C. And I need my dy, and my dy is b cosine t dt. And we'll close the bracket. So if we clean this up, we have ab sine squared t plus ab cosine squared t dt. And we're going still from 0 to T naught. And an astute mind will see we can factor out A, B, they are constants. And we're left with sine squared t plus cosine squared t. If we do, factor that out. And we got sine squared t plus cosine squared t, which is 1. So 1 dt. Which means, ooh, if I put the t first, we've got 1/2 tab. As much as I like doing that, just to make a word, the math part of me says no, put the variable at the end. 0 to T naught. And so we get 1/2 AB T naught. For a full ellipse, T naught goes to 2 pi. And so we would have 1/2 AB times 2 pi, which is pi AB.
Is Green's theorem valid if it doesn't make a complete loop?
The thing we're going around is a complete loop. We stopped early just to show it. We could have kept going.
Well,
It still works. Because the region we're binding over, going over, it is a closed loop. And the area inside, I mean, it's still applicable just because we didn't follow the full curve. It seems silly to not follow the full curve because you should, because otherwise it seems kind of weird to say, oh, we got area by going here. That doesn't make any sense, right? I hear what you're saying. Like, why go from here to here and call that area? That's effectively what's happened at that point. Well, no. We sweep around to some arbitrary thing T naught. And so we're getting that area and not the full thing. This might be why they put in the book, I grabbed this problem from the book to point out that this is, they actually say 0 is less than T naught, less than 2 pi, to point out that it's the full curve. And it might be for the very argument you're presenting. And it's the area of the ellipse is much like the circle. Circle is pi r squared, but the radius changes on an ellipse. So it's pi AB. Let's see, where's the next one I want to do? All right. Let's take a look at one more thing for 15.4. We want to evaluate any closed path C in the field 4x cubed y and x to the fourth. Any. So we have the line integral f dot dr. Minus df dy dA. And since the path is not specified, the left side really isn't helpful. I mean, we could come up with any path we wanted to. I put dA there. That is not correct. That is dy. We could come up with a path and roll with it, or we could just deal with the right-hand side. So let's do that. So what is, remember this is F and G, and I need to pause. Wait a second, Jones. Let people write the problem down. So, sorry, Lawrence.
Maybe give them a chance to try to solve the problem themselves.
Yeah, we got time for that today.
Oh, I see what you're talking about. Oh gosh.
What?
What do you mean God? You're getting 0.
Okay.
That's interesting.
What's wrong with that?
We'll see.
Do I get 0? Let's see what I get. So G is x to the 4th. So dg dx is dd dx of x to the 4th, which is 4x cubed. And then we need df dy. And that's ddy of 4x cubed y, which is 4x cubed. Which means the closed loop in that vector field without defining the loop is 4x cubed minus 4x cubed ds, which is 0.
Oh, that's it? Okay, awesome.
That's it?
And it's interesting to note that while this is also 0, this is also a conservative vector field, isn't it?
We could test it.
Well,
Yeah, f dot dr equaling 0 should mean it's a conservative vector field.
There's your physics of the day line.
Which means it's probably coming from x to the 4th y plus c. That's me doing some quick integrating, but since we are trying to connect all the topics here, he's right. When the closed loop integral is 0, this is a conservative vector field. So why don't we find the potential function I was just talking about? So find fee is your next task. And if you don't remember the equation, F is the gradient of phi. I will be at Starbucks both Saturday and Sunday.
Life. But don't even think about it. We will do it after.
And as far as I know, I'm not leaving town during Thanksgiving week. If I do, it would be to go see my brother in San Jose for the day, and I'll be back. I will be doing stuff at Starbucks that weekend, next weekend as well. If you're around town and you want to stop by, just let me know. And if you're feeling really like I want to do some extra work, I'm available Wednesday next week. Let me know and I can meet you at Starbucks on Wednesday.
Thanksgiving at Starbucks with Mr. Jones.
All right, so the gradient of phi is df dx dg dy. And in fact, that is part of the reason why it is you can see when you do Clause's theorem with dg dx minus df dy, why that equals 0. In fact, let's look at that at the end. So F is df dx, not F, phi. F is d phi dx. And so we will integrate both sides with respect to x. And I get phi of xy on the left equals x to the 4th y plus some constant, but constant with respect to x, which means this could be a function of y. But we know what d phi dy is, so let's just take I almost said time derivative. Let's take the derivative with respect to y. We'll do d dy now of both sides here. And I get d phi dy equals x to the 4th plus h prime of y. And that should equal my x to the 4th from up here. Which means we subtract x to the 4th from both sides, we get h prime of y equals 0. We integrate both sides with respect to y, and we get h of y is a constant. And we'll plug that back in up here. And so we'll get phi of xy equals x to the fourth y plus some constant.
That last constant, is it like a constant in terms of y, or is it just a constant? It could be x or y variables.
It's a constant period. H of y was only a function of y. We've already dealt with x. It was only going to be a function of y, and we found that its derivative with respect to y was 0. So there's no y in it. So it's just a constant number. It's a value. There's no variable in it. This is, I'll write out the step a little bit better. Here, we know it's 0. So if I integrate both sides with respect to 0, or not 0, dy, this gets us back h of y. But the integral of 0 is a constant value. With respect to y, the x has already been addressed. I mean, if you're curious and you're not certain, if you want to put plus g of x and go back in and do the derivative again with respect to x, and you'll see that g of x would have to be 0 also. Or another constant.
Yeah, what's happening more?
So you'll get h, y, and c. Where I was going with this is how part of the reason why conservative vector fields have a closed line integral of 0 with the Green's theorem. Let's just take a look at this. d phi dx, d phi dy is f and g because it's our f, right? So let's look at the right half of Green's theorem. dg dx minus df dy. dg dx is d squared. I wrote theta phi dx dy. That's dg dx. And I'm just looking, maybe I should get rid of the integral because I don't want to write the whole integral there. Df dy, well, f is d phi dx. So if I do the derivative with respect to y, the dy goes on the outside, and then we've got d phi dx. So d squared. But by Clairaut's theorem, good old Clairaut, those two are the same. And so we get dg dx minus df dy equals 0. And that's why. What?
Yeah. It doesn't matter the order you take in reserve the.
It's on the order, it doesn't matter what order you take a partial
It'll be the
derivative
same.
where f of
Oh,
x,
that's
y is
plural.
equal
That's
to
plural.
f of
Yeah,
y.
we did this back in the
Oh, I
derivative
see.
chapter.
Alright,
This was
alright.
Clairaut's theorem.
I don't believe that. You just couldn't remember the name of it. That's all.
Yeah, that makes.
So that equals 0, which means the closed line integral we got up here, f dot dr, the right side is 0. All right, let's take a look at 15.5. We kind of took that and tied everything back in from 15.4 on before. With Green's theorem, we added in, looked at conservative vector field. We looked at potential functions. That was a good wrap up right there for previous stuff. Let's take a look at 15.5. And I've got the equations written down in case you have not looked at them. Well, I've got two of the primary equations written down. So we've done surface integrals before in chapter 14.4. Well, surface integrals really two-dimensional integrals, but in chapter 14, we did not have this. This is a chapter 15 exclusive brought directly to you by Anton and friends. Yeah, I know, I'm a dork.
Has tried that. I was gonna say. Why the best.
So, this should look familiar. The square root of z, well, in the past, I did dz dx squared plus dz dy squared. Dx dy. That should look familiar. That was chapter 14. That shows up right there. Then we also did this part, which is less familiar, but stuff we still did. So that's the old stuff. Now we're adding in a function in front of it, but the process hasn't changed. If you skim ahead, you will see in 15.6, 7, and 8, we are doing double and triple integrals and physics topics. Some physics topics, it's not all physics. But you'll at least see something that if you're like, I want a reason for doing this, you'll have a reason for doing this.
There's a good bit of physics applications, but does it mean everything in 15 is physics?
No. But physics helped push many of the ideas to development. Like 15.6 is on flux. It's a use of surface integrals. It's probably why some of this stuff was developed.
Just learn use. I saw that video, but like, it's too easy to
Integrate over anything. Even infinitely.
There are two other variants of this red line. That's for this one, we've got z as a function of x and y, but you could do x as a function of y and z, or you could do y as a function of x and z. The formulas are similar. If you want to see them, they're in the lecture videos. I hope you guys are watching the lecture videos. I haven't looked to see how many people have watched them. I get depressed knowing that there's 30-something students and only seeing 15 people watch the videos. But maybe my pass rates at the end of the semester will reflect that. So we are going to evaluate this.
This guy. Sometimes it's weird. Like sometimes some of the random videos will have like 47 views. I'm like, what? They go from like 6 to 47.
Right.
Like, some people just
For those, I wonder if it's the same person rewatching them.
I think YouTube's just broken. I see the videos on my YouTube page and I just scroll past. It's like recommended. He's like, nah. Yeah.
So what, before I even tackle this problem, can anyone tell me what R is? What else where else we've seen this? You've seen this. You have not seen this with U and V before, but you have seen this.
Oh, it's a fucking identity. It's sign you. No. That's the same. I don't know what you're talking about.
right?
Yeah.
The only difference here is rho equals 2.
Fair.
It's a sphere, right? Sneaky, huh? Maybe I'll leave that up. It's good to think ahead. Or good to make connections where you can, but we're not going to use phi and theta. We're going to use u and v. So we need to follow this formula. We know what it's going to end up being, though, because we know if it is phi and theta and rho, normally we would have rho squared sine phi. So I'm anticipating we get 4 sine phi here. But let's just make sure. We don't have rho in the equation, so we're not doing the full triple integral. But let's take a look. So I need R of u and we need R of v, and we're going to do the cross product form. So I'll just start setting that up now. So R of u is 2 cosine u cosine v. And then 2 cosine u sine v. And then negative 2 sine u.
Bless you.
And if we do RV, we've got negative 2 sine u sine v. I've got 2 cosine u cosine v. I really don't like the way this is looking. And then we got 0. I got I, J, and K unit vectors. So I'm going to try to put little parentheses in there, make it look a little bit better. It looks like shit right now, at least to me. Let's wrap that turd in gold, make it look good.
Yeah, cool.
And we're going to need the magnitude of this when we're done, but we're not there yet. So what's our I component? 0 minus, which is a plus 4 sine squared u cosine v. And then I've got negative j hat. That component is 0, and then we've got a minus. I got a minus outside for the j hat. Minus 4 sine squared u sine v. And then my k hat isn't the prettiest thing. There is 4 sine u cosine u cosine squared v. And then I got a plus 4 sine u cosine u sine squared v. And hopefully you see this has some common threads, components. If we factor that out, we're left with cosine squared plus sine squared, which means k simplifies to 4 sine u cosine u. Let me pause and let it digest. And I already know I'm gonna need another damn whiteboard because this is a long problem. So that's my RU and cross RV. Now we need the magnitude of that. So I've got 16 sine to the fourth u cosine squared v. That's my I component squared. What did I do on J? There's a minus inside there that I don't have. There we go. And then we've got our J component, which is 16 sine to the fourth u sine squared v. And finally, we've got 16 sine squared u cosine squared u. And all of that is under a radical.
Are you guys enjoying surface integrals yet? Aren't they fun?
The pain in the ass with this one is it's spherical,
Yeah.
right? That's what's making this tedious. It's long.
Yeah.
But I already know how it's going to turn out because I know what it looked like. I identified right away this was spherical. I was thinking outside the box. This is from the book. I don't know why they tried to get sneaky. So, what can I got 16 on all of them. If I pull out the 16, it's 4 on the outside. And I've got a sine squared u in all of them. If I pull that out, that's a sine u on the outside. And what would that leave on the inside? I've got sine squared u from this one and this one, which leaves me cosine squared v plus sine squared v. And I pulled out a 16 sine squared u there. So all I have left over there is cosine squared u. So I will write what came out. We pulled out a 16 sine squared u. That's what became the 4 sine u. So divide all of those by 16 sine squared u. And we can see that goes to 1. And we're left with sine squared u plus cosine squared u on the inside. And that equals 1. So the magnitude of RU cross RV is 4 sine u. Does that match up with rho squared sine phi? If we look up here, phi was u and rho was 2, so that does match up. But we're not done. So we are doing the surface integral of e to the negative z dz, not dz, ds. And we are using our formula up there. I'll rewrite the formula. This is the generic form is f of uv ru cross rv to u dv. So where is that equal here? E to the negative z is my f. I need to write that in terms of u and v. Z was 2 cosine u. So this is e to the negative 2 cosine u. And then I've got my RU cross RV is 4 sine u. And then I've got du dv. And they gave us the limits of integration. U, which is the inner integral, goes from 0 to pi over 2. And v went from 0 to 2 pi. So not a full circle. Half a circle, or not a full sphere, half a sphere. That makes the negative 2 cosine u look like it's part of the pi over 2. There we go. All right, so that's what we're integrating. I'm going to do a w sub. I would use u, but we already have a u. I'm going to say w equals negative cosine u.
Wait, is this is one of those cases where you can split up the integral like they're being multiplied or something, right?
We can, yeah, because there's no v's. So we can do that, definitely.
Does that make it easier or does that make it harder?
It will make it easier. I want to, right now I've got u's in the exponents and outside the exponent. I'm going to clean that up first and then we'll look at separating it. But yes, it will make it easier. At least I think so.
Bless you.
And what happens when u equals 0, w equals negative 1. And when u equals pi over 2, w equals 0. So if I rewrite my integral, I'm going to bring that 4 out front. I've got negative 1 to 0. And then we had e, this should be 2w up there now. And the sine u and the du turned into a dw. And then we got a dv. And Lawrence spotted something that'll speed up the problem. I don't know if that makes it any easier, but it definitely speeds it up. This is the limits of integration have no variables in them, and we have no plus sign or minus sign in our function. This is separable. So I can turn this into 4 times 0 to 2 pi dv. And negative 1 to 0 e to the 2w dw. So we've got 4v from 0 to 2 pi. And we've got 1/2 e to the 2w from negative 1 to 0. I think this does make it easier. I think if we had done dw first, we're going to have e's floating in around in there. We're more likely to make mistakes if we don't separate it. So that's why I think it's easier. I think separating it makes it less error prone. We can see this gets us a nice fat 8 pi. This gets us 1/2 e to the 0 is just 1. Minus 1/2 e to the negative 2. I guess I could put the 1/2 with the 8 pi over there. And we've got 4 pi times 1 minus 1 over e squared. And I'm feeling pretty good about that, unless anybody saw me do something wrong. Normally someone says something for now, so if I made a mistake, I suspect it's in the last little bit.
I see no apparent mistakes.
What, Brandon?
I see no apparent mistakes.
What I mean?
Like, I don't see anything
Like
that's,
obvious, it means like,
Yeah.
this jumps out.
nothing that jumps out.
Or time. Word. Yeah. That reminds me.
So I'll be recording the 15.6 videos today and hopefully 15.7. I plan on having 15.8 by the end of this weekend as well, and I'll be grading the test this weekend. If not on Friday. If you want to come to Starbucks, let me know you'll be there. I assume Eric's going to be there, so I'll be there. And then we can talk about Thanksgiving week next week. See if anyone wants to show up during the week. Other than that, have a good weekend.
I have my SIRs from 4 to 5 tomorrow. Not
And can I
AM.
just ask, are we having fun yet?
Yes.
Now is my request that.
You guys said no. Well, depends on what do you mean by fun? You mean how much fun these problems are, or how much fun the spot is?
I'll take either.
I'll take either.
Oh, hey, John,
Yeah,
I sent you, I got
I
inspired
saw you
last
sent
night.
me something at like 11:45. I haven't looked at it yet. I saw it this morning.
Yeah,
What'd I
I got
say?
inspired. I was like thinking about my personal insight question when I was in the shower, and I was like, oh, I got a perfect idea for one of the questions. And then I just
All right.
wrote it out. So,
I will,
yeah.
I'll read through that shortly and give
All
you
right,
feedback.
thank you.
Uh-huh.
Cool.
All right. Nobody has any questions. I shall sign off.
See ya.
Later.